Good morning, everyone, and welcome to our webinar on streaming seismic data in the cloud. Today, we are going to discuss how you can turbocharge your seismic data with Bluware VDS and Bluware FAST. This is a part of our webinar series with Microsoft. In our previous webinar, we showed Microsoft's Windows Virtual Desktop technology and how high-intensity 3D visualization applications can be run in the cloud. And today we're going to talk about delivering that data into those applications. Let me first introduce to you Andy James, Bluware's Chief Product Officer. He will discuss data compression, storage, and how to stream data into your applications. Then Andy will pass it over to Kadri Ume, Principal Program Manager of Azure Energy, and he will discuss Azure and the Open Group OSDU platform in more detail. So Andy, I'll go ahead and let you take it away.
Thank you, Alex. I appreciate the introduction. I'm really excited to share this topic with you today. What we'll be covering, as Alex said, is about VDS, and then we'll look at our FAST technology, which I'm really excited about. And if you're beginning your cloud journey, this is all possible today with Azure and OSDU. The topic that I'm most passionate about is seismic data in the cloud and how we can make that usable. This is possible through Bluware VDS. But let's start with some basics. What is VDS? VDS is a simple acronym that means volume data store. But VDS is much more complex than that. It's a highly advanced system for storing any form of signal data. We just happen to use it for seismic data. But when we access VDS through the Bluware VDS Access Engine, we're able to achieve even the most intensive workflows, such as deep learning, or as I'll share with you today, data streaming. But let's talk about some fundamentals. VDS is a brick format, and as you know, as an interpreter, brick formats have been around ever since 3D interpretation has been begun. But it's how we use it with all of the other capabilities that I'll share with you today that make it possible. And we can provide instant access to any part of the VDS, not just the bricks, but even within the bricks, we can access these layers very quickly. So whether it's inline, cross-line, time slice, cube, or any random slice, which we use for interactive deep learning, all of this is achieved through VDS. VDS is API based, and the APIs enable fast access to metadata. So it's possible to read things like the trace headers of a seismic survey without opening the entire data set. Simply read just the parts that you want. The Access Engine enables very fast queries across brick boundaries as well. So you're not just limited to querying the bricks. There's two storage formats for VDS. One is file-based and the other is cloud. The files are really good for traditional file systems on-premise, but it also makes them portable for things like transmitting data from acquisitions. VDS Cloud has been optimized to use cloud object storage, such as Azure Blob Storage, making it highly cost-effective and massively scalable for cloud digital transformations. The beauty of both of these formats is they're all accessed through an identical API. Just how you connect to them changes. So how do bricks translate to blobs? Well, in your Azure subscription, you start with a storage account. VDS is contained as within an Azure container, and then millions and millions and millions of blobs represent chunks of VDS. These could be tiles in 2D data or bricks in 3D data. The beauty of Object Store is the ability to asynchronously read this data through APIs. And this is where we get much of the performance. VDS can support levels of detail, which makes it ideal for visualization, such as 3D visualization. It also supports up to 6 dimensions, making it ideal for things like 4D seismic data. And it supports unlimited numbers of auxiliary channels as well. So VDS is potentially limitless. You can store any type of EMP data types within it that are appropriate, such as seismic lines, pre and post-stack surveys, attribute volumes, geobody volumes, and regularized single Z horizons and heat maps. From a size perspective, it's virtually limitless too. We tested it on a 16 terabyte data set without any performance degradation. When you take this limitless potential and put it to use, the API access makes it ideal for data science who want to access this through Python and other APIs. The bricked format is ideal for 3D interpretation, and compression makes it ideal for moving data across continents or for new seismic acquisition. Fast random access makes it perfect for deep learning and high intensity compute functions. Cloud-ready formats, such as the Object Store, supports any organization's digitalization goals. And an OpenVDS implementation of the API makes it vendor neutral. So anyone can build on VDS without having a commercial contract. One of the key features of VDS is Bluware's adaptive compression. Our original survey data is represented here by 100%. Our unique true lossless compression can reduce storage by about 25%, but it also maintains the original data inside of it. So you can round trip your data to an MD5 checksum version of the original data. So think about that, reduce storage by 25%, but contain the original format within the data itself. This is a truly unique feature. Our streaming technology enables us to deliver any level of compression into a client workflow from the original data without storing multiple copies. And I'll talk a little bit about adaptive streaming shortly. Our compression has been tested across many different industries too. And here is a typical amplitude spectrum. Now, note this is 2 millimeter raw shot data, so it's super high frequency as well. The compression levels are really good, but I'm going to zoom into each side so you can see this a little bit closer. On the left here, this was the original graph. On the left here, you see the lower extents, the lower frequency data. And all the way up to 17x on this 2 millisecond data, the line tracks almost identically with the original compression. And it's not until you get to about 195 Hertz that the 17x compression starts to detract, making it ideal for processing type workflows and early access to data. Our adaptive streaming technology allows you to store VDS in Object Store using true lossless, yet the client can access any compression level. So for example, web visualization doesn't really need a lot of quality and is perfectly adequate at 40x or potentially even greater. whereas a computation may need much more quality. And this is all controllable by the client. I liken this to watching a movie on Netflix. If I watch a movie on my phone, I don't need as much information. But if I watch it on a 4K TV, I want as much information as I can get to get that maximum experience. VDS adaptive streaming uses the same basic principles. So the benefits of compression are it's industry approved. We've had approval from major oil companies, seismic processing companies, national oil companies, independent software vendors, cloud technology providers, and also experts within other industries such as medical, test our compression, and they all come back validating the quality of the compression. It's also benchmarked and delivers extremely high performance as well. We tend to use the fastest decompression, and we deliver the highest compression ratios for similar quality or higher quality at the same compression ratio. We have made our compression available for a free-to-use implementation called OpenVDS Plus. I'll tell you a little bit more about that later. And our true lossless technology is unique across any adaptive compression and supports zero loss on round tripping of data. Adaptive streaming allows the clients to use any level of compression without storing multiple copies of the source. It's also true serverless. Now, let me clarify, serverless, we don't mean it requires serverless infrastructure in the cloud, which runs code. It really is serverless. VDS Cloud doesn't use any code in the cloud. It just sits on object store. So while it's sitting there, the only thing you're paying for is storage. This reduces the cost of any code running in the cloud, any infrastructure needed to operate VDS, or any infrastructure personnel to support it. We do this through the data access engine. Most scientific workstations have pretty beefy capabilities, and the access engine exists on the client, delivering the workloads into the client application. So whether you're accessing VDS Cloud or VDS File, the engine is running on the client and accessing the data. This makes it even more cost effective because you're running it on a workstation that you already own. The access engine has some key features. It's random access. The engine knows how to request just the information that's needed for a particular client requirement. Prediction is implemented through the engine, and it interprets what the user wants and prefetches information before the user needs it. So if you're traversing through a seismic volume, the engine is predicting that and bringing data into the buffers in advance. It's GPU optimized. If you have a GPU, we make use of it. If you have multiple GPUs, we'll make use of all of them. But it also scales with the machine as well. I quite often use the Python APIs on my Surface device, and it works perfectly fine because it doesn't lean on the GPU in that particular device, and it's not an NVIDIA-based GPU. So it scales up and scales down to your particular machine needs. Now, I mentioned OpenVDS Plus earlier and also OpenVDS, but I really want to clarify something here. There is only one VDS, and VDS is what I've been talking about up to now. The APIs, however, are different. Bluware has a commercial API for VDS. There's OpenVDS and there's OpenVDS Plus, and these have slightly different implementations. So let me share some information about what they do. OpenVDS is a true open source implementation. We distribute the source code and a binary on GitHub. So you can get access to this today. You cannot create compressed data in OpenVDS, but you can read any VDS, whether it's been created through VDS commercial APIs or VDS Plus. You can actually read any data. It doesn't include the compute engine as part of it. Simple read access, simple write access. There's C++, Python, and Java APIs available, and it really serves to document the structure of VDS so that if you decide to put your data in VDS, you know that you can get access to this data forever into the future. It also helps to drive community adoption. We're always surprised about new implementations on OpenVDS that we have no idea about. And this is a great part of being in the open source community. And it means there's no vendor lock-in. OpenVDS is a freeware implementation and is distributed as a binary, but this does allow you to create compressed VDS. So anyone can download this binary and create compressed VDS as they need to, or implement it into their application. Once again, this doesn't include the computer engine, but it does deliver our industry-leading compression to anyone that wants to use it. Our commercial full engine is all of the bells and whistles, and this includes the compute engine, which accelerates the data information that can be driven into applications. This enables us to create interactive deep learning workflows and also high performance interpretation and on the fly computations. So this describes the different implementations of VDS and the VDS APIs. So the combination of this brings new possibilities. We use VDS to stream millions of images into TensorFlow, and this has enabled us to create interactive AI. Interactive AI eliminates data preparation, making deep learning truly an interactive experience. That interactive experience delivers new insights to interpreters and reduces time to certainty. VDS streams any seismic data into legacy applications, including pre-stack, and has enabled us to build Bluware FAST, which eliminates expensive storage infrastructure, allows you to create an entire data library of seismic data that's online, and reduces data duplication by copying individual files down to workstations, enabling true cloud digitalization to be achieved. So that's where I'm going next, to talk about a data delivery workflow in Bluware FAST. We've all seen a transformation of how we watch TV, but the reality is we don't. We all watch TV in exactly the same way. There's a screen showing images, and we watch those images. What has changed is how we deliver those images into your eyes. So Bluware FAST is like Netflix for your seismic data. The data the user wants is streamed to Bluware FAST and delivered into a format that the application can use. In addition, you have access to an entire library of content. Imagine all of your seismic data available to you in the cloud and streamed into your workflow on demand. FAST uses transcoding technology to read data stored in an Azure Blob Store in VDS Cloud, which is delivered directly to the workstation. we on the fly transcode that information directly into the application format, and we stream it into the application. The application thinks that it's reading from a file, but actually behind the scenes, it's reading directly from the cloud. So the data never touches disk. Let's look at a typical fast workflow. Our single source of data is stored in a centralized library and object store. It's delivered to applications as needed. Applications require their own format. They might require specific performance optimizations, for example, inline, crossline, and slice optimizations. Some applications require smaller amounts of data, such as subvolumes. We present all of this information as a virtual folder on the operating system, which we call the FAST virtual folder. This is presented as virtual files. The interpretation application reads from those files just like it would today, which means that the application doesn't have to be changed to use this integration. I've used FAST with applications, free applications like SeisC to read SegWide data. SeisC has no idea that the data is being streamed directly from the cloud. Now let's look at a data workflow for seismic interpretation. We start with a post-stack survey, which today could be anything around 200 gigabytes, all the way up to 600 and potentially even more. In order to do interpretation, we need that information in application formats. So Petrel might need a copy. PaleoScan may need a copy. We may want a SegWide. We may need a raw version or some other format, depending on what flavor you're using. That adds another 800 gigabytes before you even start work. Performance optimization to need in some applications. PaleoScan, for example, likes to work in 3 different directions for efficiency's sake. So we may need to add an offline, an inline, crossline, and also a slice. That adds another 400 gigabytes. And many of these applications work really well if you break things down into subvolumes. So for this example, I've taken 4 subvolumes for each of those volumes, which adds a whopping 1.2 terabyte. The result of this is a data duplication from that original 200 gigabytes into 2.4 terabytes of data to support an interpretation data workflow. FAST eliminates this by streaming all of that data into the applications and never writing the file to disk. Let's start looking at cloud storage costs. To store a petabyte of data in the cloud per month, cloud storage can be quite cost effective if you look at archive. The challenge with archive is not usable. You have to restore the data to make it usable. All of this information is available on the Azure calculator as well for you to look at. When you need to use the data, typically you need to copy it into a file system. So comparing a couple of different file systems, and this represents what you typically have in your on-prem environment in the cloud, these file systems become up to 20 times more expensive than the blob storage or the object storage that you're using. So that's great, but let's look at this in practical example. And here I want to show you through a video workflow of how FAST works in practice. So the first thing I'm going to do on this Azure VM is open up my computer. I have an operating system and I also have a temporary storage. I'm starting the FAST service and you'll see that our virtual disk suddenly appears. This disk is empty at this point because I haven't mapped any files. In this example, I'm going to use a Python API to do this because I want to actually do quite a lot of mappings to show you through the workflow. In this simple Python script, I do some connectivity to the APIs, and now I attach to the source. This is a 200 gigabyte data set stored on Azure Blob Storage. Now, as I step through this, the next thing I'm going to do is create a virtual segue. Now, what this has done is created a relationship in FAST between that mapping and created a virtual file. You see this folder has appeared. You can create any structure here. And now I have a segue file. I haven't created it on disk. I haven't copied it on disk. I haven't even read it at this point. Let's create the 3 other formats that I talked about. Give me a total of 4. And I'm also going to create the subvolumes that I mentioned earlier. This represents that diagram I showed in the PowerPoint. Now, as I go to the folder here and do a refresh, what we'll see is virtual implementations of all those versions. There's PaleoScan, there's Segway, there's ZGY. All of these files exist here. Now, when I look at the folder, 2.37 terabytes of data is available. I do not have that disk on this machine, but I can read these exactly like a normal disk. So next I'm going to go into an application and see the experience here. I want to thank Elise here for providing us constant support with how to implement this into PaleoScan, but they didn't change their software at all. You can see the survey here, and which I can bring up a slice of, and I'm going to just zoom into a particular region and change the color bar. Everything in the application and the user experience, even the application itself, remains unchanged. This is a slightly older version of PaleoScan, which was not changed to work with FAST. So here I'm going to create a horizon. Now, I'm not an interpreter, so please don't critique my horizon picking skills here. And what I'm going to do is just pick on a horizon, scroll through a couple of different sections here, and just show you that the data access is performant, and I can use the application in exactly the same way with no change to the user experience. So once I've selected a couple of horizons here, I'll go ahead and propagate this and show you what the experience is like. So the benefits of FAST are it enables you to create a single source of data and centralize your library in one place on low-cost object store. It eliminates disk cost by having to copy data out of object store onto file systems. Instead, streaming the data directly into applications without them being written to disk. The transcoders allow support for any format, as I mentioned, ZGY, PaleoScan, Segway, SEP, and other transcoders can be implemented through plugin architecture. The system provides a backward compatible experience because the applications are simply reading data in the same way that they would normally. And also it provides backward compatibility to the end user as well. The way they actually open data is very similar to what they do today. We see a performance boost as well. Streaming in many cases and many workflows, because of things like predictability, is often actually faster than reading the data directly. And because the application is only seeing what it needs at the particular time, then the data access can often be faster. And we benchmark ourselves against the local solid state drive on the virtual machine. And with that, I'm going to hand over to my colleague, Kadri Ume, who is Principal Program Manager for Azure Energy.
Thanks, Andy. So we've been going through the cloud journey for quite some time, and we've been busy in the last couple of years to move workloads to the cloud. But Seismic is one of those workloads where probably you need to think a little bit different. Not only it's a technical enablement or a technology component problem, but it's also things related with price, performance, and usability and those kind of things. So in that manner, we've been working with Bluware for some time to enable those new Lego blocks on Azure, if you may call them, to enable easy migration and operation of Seismic workloads on Azure together. So we've been working on a few ideas to think it in a different way. Now, you've seen these kind of slides like why cloud, and most of you have already been taking the decision to move to cloud. But I just want to put a few more different things that are happening recently in the cloud migration. So I think one of the fundamental differences that we have with the cloud is scale. So by limitless, I mean not only limitless in terms of the number of VMs that you can spin off or services, but also in the type of services and applications that you can use. So by providing your data on the cloud and then providing an infrastructure to serve it up in the most efficient way, then you can access that data through a lot of services that's been put on the cloud by the day. So you can do things that has not been possible before with the scalability. The second thing is the cost, and again, Seismic is interesting in that manner. So the fundamental assumption probably when we started cloud migrations were if we get the VMs as is and if we put them on the cloud, the cost would be lower, and in some cases it's been proving that that was not the case. So again, with Seismic, we work with Bluware on these technologies that also can enable the lowering of price performance by using native cloud capabilities while providing the legacy applications to continue to work seamlessly. The third pillar, and this is getting I mean, much more interest nowadays is the sustainability perspective. So Microsoft has been carbon neutral since 2012 with its Azure operations. We just announced that we'll be carbon negative by 2030, and there's a lot of investments going on to achieve that. We just announced our sustainability reporting and showing the progress in that. And most importantly, by 2050, we will remove all of the carbon that we have emitted since Microsoft was founded. So by using cloud, you can directly take advantage of this sustainable IT infrastructure and reduce your carbon footprint. We've released something called the sustainability calculator, where you can look into, we measure the scope 1 to scope 3 emissions profiles for your services running on Azure, and then you can have a dashboard where you can look into what your carbon footprint and how much you're reducing it. So you have a significant reduction in your carbon footprint. And then probably the last thing is the security. Again, if you look into the amount of security signals we get, like every day, it's close to 8 trillion. And we have a whole artificial intelligence network that's looking into these 8 trillion attacks that we're getting by the day on the Azure data centers. And we're spending billions of dollars in mitigating them. So again, you need you have the much needed security support by running these workloads into the cloud. And as I said in the beginning, moving Seismic workloads to the cloud needs a different way of thinking. For most of us, this is where we stand. So we do have a bunch of files on tape. Most of it sitting on tape, rotting somewhere in a salt mine, and then we do have our active data on disk, accessible and this is pretty much what it looks like. And the first step in migration, as I said, the assumption was, okay, let's get the VMs or let's get the servers running on our data center. Let's move these onto Azure or cloud, and then let's try to run them. So you basically get your applications, you lift and shift them to run on the cloud, and then you provide, especially with Seismic, where there's a lot of data, and then you cannot move the data back and forth between clients and between the data centers, or between the cloud and the client. So you put these VDI workstations on the cloud that access that data, and then you basically lift and shift the data to a similar network attached storage infrastructure that you used to have on-prem. And that was the first step in migration. And while this can technically deliver and the performance is acceptable, then if you look into the price performance, it's usually not acceptable. So I think the future of seismic data on the cloud, and especially from a price performance perspective, is really being able to use the cloud native data streaming, be able to use the standards and the API, and then also be able to use cloud native capability. So I really like the Netflix analogy here. So it really boils down to, and then while doing that, you cannot just get the 200 gigabyte SegWi file that sits in a network attached storage or some other infrastructure, and then copy it to Blob and then expect it to perform. So there's a couple of complexities. One, absolutely, is the performance, and second is there's hundreds of legacy applications that you use day by day, which doesn't know how to read data from a blob because they were written like tens of years back. They expect a file sitting in a file share. So what we see is the future is basically a high performance structuring of this data that can be served in a performant way from the blob storage like VDS, a smart index where you can find your data. So similar to what we've been doing with OSDU and finding your data, and which redirects you to the right shard that sits in the blob storage so that you can read and stream it. And then also in the front end, an infrastructure, a component like FAST, which could act as an agent to surface the data sitting in a blob, so a legacy application in a file share. So that's for us what the future looks like, to deliver seismic data and seismic services in a price performant way on the cloud. So next, please. And the good news is this is possible today. So we do have, as Andy has mentioned, we did embed and integrate OpenVDS as part of OSDU, and now with OpenVDS Plus, you have the compression capability that you can do, and as you mentioned, OpenVDS is open source. So already in your OSDU deployments or OSDU pilots, you have these components as part of that deployment. So you can go in and test it and have the VDS component and test it with VDS. So it's not something that needs to be started from scratch, but it's actually part of the OSDU deployment. And with OpenVDS, you can even go and look at the code on ingesting the data and then reading the data from the VDS and how to access the VDS services. You can upgrade it to VDS, the normal VDS implementation, and with FAST, you can directly expose your OSDU data to any client application. As I said, as Andy has mentioned, there's a set of connectors, but there could be other connectors that could be built. So now you can expose your OSDU data directly to legacy applications easily through the VDS and FAST connectivity, while you can use OpenVDS and OpenVDS Plus through things like Jupyter notebooks or other artificial intelligence tool sets easily to read and write the data. So if you're having an OSDU deployment, OpenVDS and OpenVDS Plus is already there, and then we can always test these use cases easily by working together. So next, please. There's a couple of things we can do. As I said, if your company participates in OSDU, reach out to your OSDU champion. There's OSDU deployments that's ongoing with Azure in most of the operators. So if you're doing an OSDU deployment, reach out to your IT teams or your teams that's doing data teams that's doing the deployment. We're working with ISV and SI partners for OSDU services. I've put a link where we have a service offering together with vPro. So feel free to reach out if you're working with those SIs. You can schedule an MTC session. We have a Microsoft Technology Center that's based in Houston. We used to have face-to-face sessions there, but now we're delivering virtual sessions, and we have the Bluware and OSDU as part of that offering. And then you can also reach out to the Azure for Energy or Microsoft Azure sites, which I provide a link here, where you can get further information about that. So with that, I'll hand it over back to Andy and Alex for questions.
Thank you, Kadri. We will open it up now to our quick Q&A session. You can simply submit a question in the Q&A session on Microsoft Teams. I've left an announcement on there if you can see it. We will be recording this webinar, so stay tuned if you'd like to share it with your colleagues. It will be available later today. And also, please stay tuned for Microsoft and Bluware's next webinar as a part of this series in Q2. So we'll open it up the floor now to Q&A.
Thanks, Alex. There's already some great questions coming in. The one thing I did want to clarify is OpenVDS Plus is available in the next couple of weeks. It's not quite available yet, so we will be sending out an announcement. So keep an eye on our LinkedIn as well to see when that comes out. There's a really good question here. Still have to handle the terabytes of output from the existing applications. This solves a massive problem about not having to copy a bunch of data that then gets ingested into applications in internal formats. What it doesn't do is solve the other half of the problem, where the application itself then creates a whole bunch of additional outputs. There's really 20 to 30 years of legacy development in many of these applications, which have exasperated a lot of that. So there are some techniques that can help with that, and watch this space. We have some exciting excuse me, some exciting ways of using compute and moving compute server side in the future that we'll talk about in future webinars. Okay, so here's a question that's just come through. Is FAST available now? Yes, FAST is available. It's a commercially available application that is already in use today. So there's a question here about derivatives and things, and some of those derivative volumes can be re-ingested back into VDS and then streamed into other workflows as well. So for example, if you generate a probability cube or some volume in one application, and you want to make that available to many applications, re-ingest it as part of your interpretation, and then you would stream it into any application format that you might need.
Yeah. There is one question about the fast transcoders. I think, Andy, which ones are supported?
Yes, thank you. So currently we have transcoders for PaleoScan, LS PaleoScan, for ZGY format, SEP SegY, raw trace, and we also have written a custom deployment for a particular customer that had their own seismic format as well. These are API based, so writing them, for example, for Kingdom, for decision space would be relatively easy to achieve.
Probably one question, Andy, might be we spoke about like OSDU and OpenVDS and OpenVDS Plus as being part of OSDU, and I know there's a lot of companies out there that are working on OSDU deployments and projects. So what would be the right engagement model where we can test out getting OSDU data to legacy applications through FAST, and do we have a program for that where we can like work with them to enable that?
Work with different legacy applications that use different formats, do you mean, Kadri?
No, I mean it could be like the formats that we mentioned, so SegY, ZGY, or PaleoScan, the existing formats, but kind of like work with the customers who are deploying OSDU and use the tools that we discussed today as part of a pilot.
Yes. Yeah, absolutely. It makes sense to pilot. It's very easy to convert the data. With the R3 release coming up, or the Mercury release of OSDU, that really brings the whole seismic data and ingestion into play. So OSDU then begins to solve the problem of data ingestion and how it's stored and the metadata that's associated out to that particular data. You mentioned the partnership with Wipro for deployment of OSDU implementations, and we work very closely with Wipro and Resolve Geosciences to really handle mass ingestion of data. From there, having a streaming technology that delivers that data into existing applications allows you to lift and shift those applications into the cloud as well. So it feels like the full end-to-end from your massive amount of seismic data all the way through to interpretation. The workflow is almost complete at this point. It's just a case of where do you want to start and when do you want to start. But we can do pilots without a doubt. So,
Andy, did you see these other couple of questions here from Gabriel? Does it use a proprietary protocol, or is the transfer based on UDP with error checking?
So the data access, the engine talks to the object store through the object store APIs. So there's no proprietary protocols or anything there. So we just call Azure Blob Store exactly the same way that you would if you were writing a native application to the Blob Store. There's another application here, another question here that says, once the seismic data is processed in the cloud, I believe it still depends on the app's capability on premise to bring it down and ingest it. No, this is exactly what FAST does. FAST sits alongside the application. It reads the data directly from the object store. The way it's presented to the application is a virtual file. The application opens the virtual file, which initiates the request for data. And as the application reads specific data from the file, which what it thinks is a file, FAST intercepts that request and brings the data into the application. So it's not dependent on the application changing. The application, this works with old versions of applications, as I mentioned earlier. I've tested this on SeisC, on SegY data. SeisC has no idea it's bringing data from the cloud. I think we have covered all the questions. Is that fair?
It was a pleasure for everyone to attend, and thank you, Kadri, and thank you, Andy, for all your time today. And again, stay tuned for our next webinar as a part of this series.